To understand unsaturated flow, we may do a step back and visit Darcy's law again, which is for saturated conditions. And that is Q equals minus the saturated hydraulic conductivity, and then delta H over L. And to draw that little diagram again, we would have here a soil and a container here. Now this all would be full of water. The soil container is full of water, and then this drips into that container here. And then our dimensions here would be the L, which is the length of our soil column here. And then this would be delta H. In general, transport can only occur if you have a hydraulic conductivity and if you have a gradient. So our gradient here is the difference of the water level here from the inflow in comparison to the outflow. If there is no difference, this becomes zero, then this becomes zero, and that means there is no flow. So under saturated condition, that's a fairly easy and straightforward relation. If the soil becomes unsaturated, it becomes a little bit more complex. And it is then not described by the Darcy's law, but then it is the Darcy-Buckingham law. So Buckingham has expanded Darcy's law to unsaturated conditions. And Q is then written as, so here we have a saturated hydraulic conductivity. If the soil becomes unsaturated, the hydraulic conductivity actually becomes a function of the metric potential. So we need to take care of that. And then we now have to deal with two different gradients. So there's the gradient in terms of the gravity, and then there's the gradient of the metric potential. So now we have the gradient of the metric potential in respect to a certain depth C, and the gradient of the gravimetric potential also with respect to Z. So if we consider a one-dimensional case where we have a soil column, then this would be Z. This part is easily solved because that here is equals 1. And that makes this equation, simplifies this to the unsaturated hydraulic conductivity times the gradient of the metric potential with respect to Z plus 1. So also here, same thing as over there. Any transport can only occur if you have hydraulic conductivity and if you have a gradient. So if we consider a little soil column here, and we look at the potentials, then so we'll set the bottom of the column, we'll set this to 0. So that would be a hydraulic potential of 0. Then our gravimetric potential looks like this, and our metric potential looks like that. So this would be the metric potential, and that would be the hydraulic potential as a sum of the two. So that means in this case, if we just leave, we take a salt sample and we just leave it set there, this terms becomes -1, and then -1 plus 1 would equal 0, so we don't have any flow. That means in order to create flow in that column, something would have to change, like on the top. So that could be that we have precipitation, which would be we would add water to the salt column, and that would create a metric potential that is less negative, which means the overall hydraulic potential becomes positive, and then we would have flow. Or the other way around, you could have evaporation from the salt surface, and then the conditions would actually become drier, and the hydraulic potential would become negative, and then we actually have upward flow. And the simplest way to describe flow is under steady state conditions. So steady state condition. That means if we consider again a salt column, then I'll maybe draw another one to make this a little bit more clear. Steady state means we would have a column and would have an influx and an outflux, and Q in is equal to Q out. So everything that goes in a time step also leaves the bottom of the column. So that means the water content doesn't change, and we don't have to take care of that. In steady state conditions, we can readily apply this equation here. Now it becomes a little bit more complicated if we have unsteady state conditions. So in a lab experiment, we can easily create a situation like this. But in a natural environment, that is very seldom and limited to maybe a short period of time and a short, really small space. So that means I'll make this 1, turn this to 2. In a natural condition, we usually have transient flow. Conditions. And that means, for example, we have rainfall, so we have a lot of input into our salt column, and then the rain stops, and the water moves downward in the salt column, and then it starts evaporating again. So we have only transient conditions, and this condition here is not applicable anymore. And it makes this relationship here more complicated, because now we have to address for the water that is actually in the column, and we have to address that. So precipitation that we add would also add to the storage of water in the column. And to describe this, we use a form of the continuity equation, and that is the derivative of the volumetric water content in respect to time equals the derivative of flow in respect to space. And that is what we consider the continuity equation. So what this means is whatever changes in time also needs to change in space. And a small example for this could be that we have two glasses. So this is glass number 1, glass number 2. They're both at time t0. So glass number 1 is full of water, while glass number 2 is empty. So now we consider a second time step. Again, we have our two glasses, and if I now would take this glass and dump half of it into that glass, then at the time step T1 we would have half full glass here and a half full glass there. So what this means pretty much is so the change in time, meaning if we look at glass number 1, the change in time is that we lose half of the volume is equal to the change in space, which is then the change that goes from this glass into the other one. That's the whole secret behind that equation. So we can go ahead and insert this equation into the continuity equation, and that leads to this relationship here. And then we have our hydraulic conductivity, and this times the derivative of the metric potential with respect to z plus 1. So this equation, that's a very important equation because this governs water movement in soils, and that is called the Richards equation. And typically we don't solve this equation. There's many different models out there, for example hydras, that help to solve this. So that means that we only supply boundary conditions and initial conditions, and then we can model how a soil performs under different environmental conditions.